Hello, my name is Frits de Mul and this is a talk about charge and current elements needed for 1, 2 and 3 dimensional integrations. This is a presentation in a series of presentations about electromagnetism topics. Why do we need current and charge and current elements to perform integrations? It's necessary to rewrite charge and current elements like dq and dy in the form of coordinate elements like dx, dy, dz using charge and current densities, because coordinate elements can be integrated over spatial coordinates. Basic symmetries: we have planar symmetry, cylindrical symmetry and spherical symmetry, and we will discuss that. We need coordinate systems. For planar symmetries we have the normal x, y, z coordinate systems drawn here. For cylindrical symmetries we have r, phi and z, r, phi and z, as is seen here. And for spherical symmetries we have r, theta and phi, r, theta and phi. Let's begin with basic symmetries for Gauss Law. For Gauss Law we need either an extended plane or a long cylinder or a sphere. For an extended plane we have a pillbox with height approaching 0. In a cylinder we have a Gauss cylinder with a radius larger than the radius of the cylinder itself or smaller, and a length L. And for a sphere we have a Gauss sphere with a radius r smaller or larger than the radius of the sphere itself. Basic symmetries for Ampere's law. We denote with an arrow the direction of the current. This is a symmetry for an extending plane with a current density along the plane, and in that case we take an Ampere circuit in the form of a rectangle with a length L and a height h, and that height is approaching 0. This is for a plane and for a long solenoid. A long cylinder has an Ampere circle with a radius r, and the radius can be smaller or larger than the radius of the cylinder itself. And here a toroid with or without a gap. Here is the current, and the Ampere circuit is inside the toroid with a length L. Charge elements. First, a thin, long wire, infinitely long and thin. Then suppose we have a charge distribution lambda of z in coulomb per meter, and if it is homogeneous then lambda is constant. And in that case the charge element is lambda times the coordinate element dz, and the coordinate element can be integrated. Again, to perform integrations, always rewrite the charge and current elements in the form coordinate elements, because those elements can be integrated. For a thin ring with a thickness much smaller than the radius and the charge distribution of lambda in coulomb per meter over the ring, and if it is homogeneous then lambda is constant, and the charge element is lambda times r times d phi, and r d phi is this element here. A charge element in a flat surface. We have a charge distribution sigma in coulomb per square meter, and a surface element dA is dx dy, and the charge element here can be written as sigma times dx dy. It's possible to have the surface shown in the form of a circular disk with a charge distribution sigma as a function of r and phi. And when we have a disk, we can divide it in rings with a radius r smaller than the radius of the disk itself, and the surface element here is given by r d phi times r dr, r d phi times dr. And if sigma is constant, then dq is sigma times 2πr dr. 2πr dr. The integration over phi is performed. Here we have a cylindrical surface, charge elements. All the charges are placed at the surface of the cylinder. Then the surface element is r d phi. That's r d phi times dz here, and the charge element is sigma as a function of phi and z times r d phi dz. And if sigma is constant, then we can integrate over phi, and we end up with sigma times 2πr dz. A spherical surface. This is a part of the spherical surface. Here we have a radius r, and the charge distribution sigma. The surface element dA is given by r d theta, that's r d theta, times r sine theta d phi. And r sine theta is this distance here, and d phi is the angle. And that's the same as this. So the charge element is sigma times r d theta times r sine theta d phi. A spatial distribution. General spatial charge distribution rho as a function of x, y, and z in coulomb per cubic meters, and this is the volume element dV. And the charge element is rho times the volume element. When we have a cylindrical volume, when the charge is distributed over the total volume, then we talk about a rho in coulomb per cubic meters. And rho can be a function of r, phi, and z. And the charge element is dq is rho times r d phi times dr times dz. Delta dv is r d phi, that's this distance here, times dr is this distance here, times dz. A spherical distribution, rho times r d theta d phi. The volume element is dv is r d theta. R d theta is this side of the cube, of the rectangle, the block. R sine theta d phi is this side of the block, and dr is this side of the block. So the charge element is dq is rho d theta r sine theta d phi dr. And if rho is independent of theta and phi, we have dq is rho times 4 pi r squared. It's the surface of the sphere at distance at radius r times dr, and that can be integrated. A general flat surface with current density J, x and y in amperes per meter. Here is the current density, and the contribution to the current element dy through the strip with a width di dy in the x direction is the current element is di is j times ex times dy is jx times dy. And that jx is the current density in the x direction. A solenoid surface. Suppose the current is over the surface and it is directed perpendicular to the axis. Suppose we have n windings with a length L, each a length L. Then the current density is, in this case, here, is tangential, and we have a J phi in Ampere per meter length, and it means that the current element is J phi dx is n times I dx over L. I is the total current times n over dl. In the second case is the current parallel to the x-axis in Ampere per meter circumference length, and that is di is jx times r d phi. R d phi is the width of this strip, and here dx is the width of this strip. In general, when we have a general current tube with a current density J as a function of x, y, and z in Ampere per square meter, and that's a volume current through the material, we have a current element dx, diz is contribution to the current in the z direction. That is diz is J times Ez, that's a scalar vector product, times dx.dy, and dx.dy is the cross-sections area, J in the z direction times dx.dy, the cross-section. A thick wire. We have a current density Ampere per square meter through the material parallel to the symmetry axis. That's here, J. The surface element is a ring element with a surface. dA is r d phi times dr, small r. And the large R, the capital R, is used for the radius of the cylinder itself. The current density then is given by di is J as a function of r and phi times r d phi dr. And this is the end of this presentation. Thank you very much.